Hello everyone, welcome to the lecture series of Microprocessor 8085. This is lecture number 18 and today we'll be learning counters and time delays. Counter we have already done in many of the programs. Definition is given. So what is a counter? A counter is designed by simply loading a register with the desired count, and either by incrementing or decrementing the counter the desired count is achieved. Like suppose if you want to count event, we want to transfer 10 bytes or maybe comparing 10 bytes, so we need to load that number 10 in any of the register, and we can just decrement the count and check whether it is 0 or not. So this is how a simple counter is designed. Now this particular lecture is of course regarding the time delay. Now time delay can also be achieved in the similar way, okay? But the thing here is that we are converting the instructions in terms of time. We will see one example, of course. So our time delay can be achieved in a similar way, while the calculation of time delay also depends on the clock frequency. So of course every instruction, it takes some finite amount of time. So when we are giving a program, a delay program is designed, so how much time is required to execute that particular delay program. So that is how a time delay can be achieved. Like suppose if you want to design a signaling system, so a signaling system, it contains of course three signals. Like we have a red signal, okay, we have the yellow, and we have the green signal. So we want that this particular red signal, it remains on for 60 seconds, and the yellow signal, it remains on for 5 seconds, and then the green remains on for 60 seconds. So we need to hold this particular LED for 60 seconds, and then this must glow for 5 seconds, and this must again glow for 60 seconds. So we need a precise time calculation. So that time calculation can also be done by using the microprocessor program that we are going to study now. Now we'll see how to design a time delay using one register. There are various ways to design a time delay. The very simplest one is by using a single register. So this is the flowchart. We'll see the program afterwards. So this is the flowchart. The first step is, as we can see, load delay register. So we need to load the count or some number in the register. Then we will decrement the register, and we'll check whether the register is 0 or not. If it is no, then again go on decrementing until it becomes 0. When it becomes 0, we come out of this. So this particular program, this will generate a time delay. So let us see one program. We'll see one program and calculate the time. So this is the required program. Let us first read the problem. To calculate the time delay generated by the following program. The frequency of the process is 1 megahertz. So this is the delay program. I have not written the memory location. As we know, this MVIC is a 2 byte instruction, DCRC is 1 byte, JNZ is 3 byte instruction. So I have not written the memory location because we are just interested in calculating the time delay. Okay, and for calculating the time delay, we must know the T states. So this MVIC instruction, it consists of 7 T states, and DCRC, it consists of 4 T states, and JNZ instruction, jump if no Z, it consists of either 10 or 7 T states. Now here 2 T states are given because when the zero flag is reset, okay, when the zero flag is reset, it will jump to up this point. So for that purpose, for that case, the T states are 10, and when there is no jump, we have 7 T states. So this is how. Now what is the meaning of a T state? We have already done in previous lecture. We have seen that a particular instruction consists of few number of T states. So one single T state. First let us see how to calculate one T state. Now it is given that the frequency of the processor is 1 megahertz. So very first thing is we will calculate how to find the one time period. So let us see the solution part. So solution. Now frequency is given as 1 megahertz. 1 megahertz is actually 1 into 10 raised to 6 hertz. Now we calculate the time period T, 1 T state, that is. So T is equal to 1 upon frequency. So 1 upon frequency, 1 upon 1 into 10 raised to 6. So this will come up. So we have 10 raised to minus 6 seconds. Now it is convenient to write in terms of microseconds. So t is actually 10 raised to minus 6 second, which is equal to 1 microsecond. So 1 t state is 1 microsecond. Okay, now we must remember this, because frequency is given, we calculate one time period. So for this particular processor on which we are doing the calculation, this MVIC 30H, it consists of 7 t states. So it will take, of course, 1 t state, as we have calculated, is 1 microsecond, so it will take 7 microsecond. But here in this particular program, we see there is one instruction MVIC which is out of loop, and we have one instruction DCRC and JNZ. These are the inside loop. So we have to calculate the delay in two parts. For the first part, how much time it takes outside the loop. So this is the time, okay, period which the processor takes outside the loop, and this is inside the loop. So we have to calculate both the things separately, and then of course we'll add this, so we get the required time delay. So let us see how we do the calculation. So total delay, we'll just write total delay equal to delay outside plus time delay inside. Okay, so this is T out, means delay outside the loop, and T in means delay inside the loop. Now T out, as we see, outside there is only one instruction MVIC. So T out is equal to, there are 7 t states, as we have seen. There are 7 t states, and one t state consists of 1 microsecond, so it is 1 microsecond. So this becomes 7 microseconds. Next is delay inside the loop. Now inside the loop we have two instructions, DCRC and JNZ, and because this loop will run until this 30 becomes 0. Now this 30 is a hexadecimal number. So the very first thing is we need to convert this particular number 30H in decimal. So what is this in decimal? We'll see this. So 30 is 0 into 16 raised to 0 plus 3 into 16 raised to 1. So this 16 3s it is 48, and this plus 0 is, so this is 48. Okay, so 48 is the count. So this particular loop will be executed 48 times. Okay, in terms of decimal, 30 hexadecimal is 48 decimal. So this DCRC has 4 t states, and let us assume that it is going on same number of times. So 10 plus 4 is 14. Okay, so this t inside equal to 14 into 48. Okay, so whatever number we get, 14 into 48, that is our delay into, of course, 1 microsecond. So whatever time we are getting, okay, so this delay inside is actually this particular number. But one more thing, if we check it, is that this 10, in case of jump instruction, we have taken that equal to 10. Okay, but of course this 14 to 40 is of course 6 for 72 microsecond. Okay. So we need to do some correction here. The correction is that this DCRC, of course, it will be executed 48 times. JNZ up will jump up only 47 times, and the last loop, and then when it's coming out, it will be only because when it's going up, it will be of course 10 t states, but when it comes out, it is 7 t state. So we need to do some correction. Okay, so this t dash in, we have to make some correction here. Okay, so that is 3 into 1 microsecond, because we have done here, we have added 10, so we need to subtract 3, so it becomes 7, the last one, only 1. So this is 3 microsecond. So the actual TIN is 672 minus 3, which is actually 669 microsecond. Now of course this 3 is very less. Even if we ignore this, it is also, it's okay. So the total is 7 plus, so total delay is T out plus T in, which is equal to 669 plus 7 microsecond. So this is actually 676 microsecond. So this is the total time delay which we get with this particular instruction. So this is how we calculate the delay. So we have this delay program, we have the frequency, we need to find one t state, and this is what we have. We need to do the calculation with respect to decimal, so we have to do the calculation in terms of decimal. Then of course this subtraction is because we have subtracted 3, because going up is 10 microsecond and coming down is 7. So we had already calculated this 348 times, so we need to subtract 1 because the last one will come out. So for that it is 7, so we need to subtract 10 minus 7 is 3, so we have subtracted this 3. So this is how we do a calculation. Now we have another technique of generating the time delay using a register pair. See, in the previous case we studied the generating time delay using one register, and we know in case of 8085 one register can hold from number from 00 to FF. So FF is the maximum count. Now suppose even if after loading FF we don't get the required delay, we need to increase the number. That is what we can do. So another way of calculating large delay, if you want to have a large delay, we cannot generate by using a single register, so we need a large number. So for that purpose we try another way, that is time delay using a register pair. So here we use a register pair, like this is a simple program. So here we have LXI B2040, so we are loading a 2040, then DCXB. Of course we know DCXB is different from DCRB. DCXB considers B and C register as a single register, okay, and this is a 16-bit number, it decrements the 16-bit number. Now what it should be done actually, like LXIB, what our common sense says that the program should have been like this, DCXB, and then we could have got this J and Z and star here and here. So what this instruction would have done, this would have been decremented 20440, it would have decremented until B would have become 0, and as soon as this B, not only B, BC would have become 0, so this count would have gone to 0000, and after such a long time BC both would have become 0, and then the processor may come out of the loop. But the trouble is that DCR instruction, of course, see in the previous case what we used was DCRC and then J and Z was used. So in case of DCR instruction, when C becomes 0, the 0 flag is set. But the trouble with DCX instruction is that DCX, any DCX, whether B, D or H, this does not set the 0 flag. Okay, so DCR instruction, whether it is of any register, it may set the 0 flag as soon as this register becomes 0. But DCXB, okay, even if B and C both become 0, the 0 flag is not set. So we need some alternate way to set the 0 flag. So here is what some extra instructions are there. You can see here, I'll just mark with red. So this two instructions, they are used to set the 0 flag. So what is done is we transfer the contents of C to A and or the contents of A with B. So this ORAB, okay, this can set the 0 flag if and only if C and B both become 0 at the same time. Okay, so because we cannot this is the only way to check the contents of BC to be 0 0. So what it is done is, here we transfer the contents of C to A. So suppose if we are just decrementing this 2040 and we are just giving this DCX DCXB, it is so it is just decrementing the register pair, and a time will come when C will become 0 and B will also become 0. For that case, what will happen? C is transferred to A, so A also becomes 0 0. Now next we OR the contents of A with B. Now because A and B both are 0 0, so the result is 0 0, and hence the 0 flag will be set. Okay, so it will come out of the loop. And for all the other values it will just go up there. So this is the loop, this is the instruction, these are the instructions which are inside the loop. So now same way, now we'll do the calculation. Okay, so again here also, if you want to do the calculation, suppose we consider the frequency again to be of 1 megahertz. So 1 megahertz, as we know, time is 1 microsecond, t is 1 microsecond. Again with the same thing, one instruction is outside the loop, so the LXIB is outside the loop, so the total time delay, is t in plus t out. So t out is actually, there is just one instruction which is of actually 10 t states, so 10 into 1 microsecond, which is 10 microsecond. Now t inside, there are lot of many instructions, but before calculating t in, we must calculate the decimal of this particular number. So our number is actually 2040, so 2040 hexadecimal. So we must calculate this. Okay, we must calculate the decimal. So this 0 into 16 raised to 0 plus 4 into 16 raised to 1 plus 0 into 16 raised to 0, sorry, plus then finally 2 into 16 raised to 3. So this is what we do the calculation. So the answer we get is 8256 decimal. Okay, you can check the answer, it is 8256. You can use a scientific calculator, do the calculation here only. Now the inside the loop, as we can see, there are this 6 plus 4 plus 4 and then plus 10. We can ignore this last one, okay, when it comes out, because it is hardly 3 microsecond and this is an enormous amount of delay. So 6 plus 4 is 14, 14 plus 4 is, so 6 plus 4, sorry, 10, 10 plus 4 is 14, 14 plus 10 is 24. Okay, so 24 t states. Okay, so the total time in is the 24 t state into this count 8256 into 1 microsecond. Okay, so we can just ignore the last part, the 7. Okay, we don't need to subtract 3 microsecond, because this is a very enormous, we will get a very large number, a very large day will be obtained if we multiply this. Okay, so we can just multiply and check the answer. So the answer what we get is 198144. Now this is in terms of microsecond. Okay, now this is actually 10 microsecond, so this is a very large number. So even if we add this, okay, so we get 154 microsecond. So it is better to write this in terms of milliseconds. So milliseconds is 198,154 into 10 raised to minus 3 millisecond. We can ignore this few digits. So roughly what we get is 198.154 millisecond, which is almost equal to 198 milliseconds. So this is the required time delay. Okay, we ignore that 3 microseconds, because 198 millisecond is quite large as compared to the 3 microseconds. So this is the actual time delay. This is what we get. So that's all for this particular session. In the next session we will learn one more technique of generating the time delay, that is loop inside the loop. Thanks for watching.